Welcome back to my YouTube channel. I'm Chinmaya L, studying in Sri Venkateswara College of Engineering, and today I'm here to discuss on the topic of closure properties of context-free languages. So let's move in. This presentation explores closure properties of context-free languages, fundamental aspects in the study of formal languages. We will examine how CFLs behave under various operations like union, concatenation, and more, providing insights into their structural properties. Introduction. Context free languages. Context free languages form a crucial class in formally language theory. They are defined by context free grammars, which allow us to generate strings using recursive rules. This allows us to capture more complex structures than regular languages. Closure properties. Closure properties of CFLs refer to their behavior under various operations. Determining whether a language is closed under an operation means if we apply the operation to languages in that class, we always get a language that is also in that class. We will delve into various closure properties of CFLs, exploring their implications. What are context-free languages? So, defined by grammars, CFLs are defined as context-free grammars, which consists of rules that describe how to generate strings in the language. These grammars are also called context-free because the rules don't depend on the surrounding context of a symbol. We will explore how these rules shape the language. Recursive rules. The recursive rules in a context-free grammars allows for the recursion, meaning that the non-terminal symbol can be replaced by a production rule that includes itself. This recursion allows for the generation of infinitely many strings and with varying complexities. So we will see how the recursion nature influences the language's structure. Example, CFLs include languages like arithmetic expressions, HTML tags, and some programming languages constructions. These languages can involve in a hierarchical structure where implements can be nested within each other. We will use examples of to illustrate these concepts. Closure under union. Union operation of two languages is a language containing all strings that are either language or both. In this case, we'll examine whether the union of us two CFLs is always also a CFL. We'll see that the union of the CFLs is indeed a CFL. And examples and proofs can be as displays. We can formally produce closure under union by constructing a new grammar that generates the union of two given CFLs, and this grammar combines the rules of both original grammars, ensuring that the resulting language includes all the strings from both, and we will explore that the construction of the grammar is as such. Closure under concatenation. Concatenation operation refers to joining two strings end to end to create a new string. Here we will explore if concatenation of two CFLs always result in another CFL. We will discover that the CFLs are closed under concatenation. Example would be, imagine in one language containing strings of A's and the others containing a strings of B's. Concatenation of these languages would result in the resulting strings where the strings of A's and followed by the B's as such. So the proof can be that we can formally prove this closure property by constructing a grammar that generates the concatenation of two CFLs, and the new grammar would incorporate the rules of the both original grammars and ensuring that the strings in the concatenated language are formed by joining these strings on the both originals. Closure under clean start. Clean start operation, like star operation, allows for the representation or the repetition of the string zero or more times. We will examine whether applying the clean star for the CFL results in another CFL. We will find that CFLs are closed under the clean star operations. Take the language containing a simple string A. Applying the nil star to this language would result in strings containing any number of A's, including this empty string. This would be represented as A star, which means zero or more than A's. Proof would be similar to the previous example. Um, we can Prove closure under clean star by constructing a grammar that generates a clean star of a given CFL. This grammar would include a new rule that allows the repetition of the original language's strings, ensuring the resulting language contains all possible repetitions. Closure under intersection. So intersection operations of two languages contains all the strings that are represented in both the languages. This property is unlike previous ones, while CFLs are closed under union, concatenation, and clean star, they are not closed under interactions or intersections. We'll explore this. Example would be, imagine language containing strings of A's and another containing strings of B's. Their intersection is empty, so no strings can be found in both. We can create examples of these intersections results in the languages and that are context free. Counter example would be, we can construct a counter example for the CFLs where intersected result in that language that is not context free. The demonstrates that the intersection operation does not always preserve the context free property. Closure under complement. Complement operators of a language contains all the strings that are not in the original language. Similar to intersection, CFLs are not closed under the complement operations, and this is the significant contrast in to regularly change of these closed under components. Closure under reversal. Reversal operations would be the strings with its characters to in reverse order. We will discover the CFLs are closed under reveal reversal. For this means that the reversal of the CFL will always be another CFL. And an example would be, this take an example of the string ABC, its reversal would be CBA. We can apply this to the entire language, and the CFL contains ABC. This reversal would be CBA. This property holds all the strings of the language. Closure under homomorphism. Homomorphism is a mapping between symbols. While we will examine if CFLs are closed under homomorphism, it turns out CFLs are closed under homomorphism, meaning that applying homomorphism to a CFL is always result in another CFL. Thank you for watching my video.